In this lesson, we will learn how nuclear stability is related to the band of stability and the neutron-to-proton ratio. 85% of all nuclei are unstable. Stability depends on the neutron-to-proton ratio, the band of stability, and on magic numbers. Let's begin by talking about the neutron-to-proton ratio. Nuclei with atomic numbers less than 20 are most stable when the neutron-to-proton ratio is 1:1. Nuclei with atomic numbers between 20 and 83 are most stable when the neutron-to-proton ratio is approximately 1.5. You can see this on the band of stability. The band of stability plots the number of neutrons on the y-axis versus the number of protons on the x-axis. The y-axis over the x-axis gives you the neutron-to-proton ratio. Shown here at a 45-degree angle is a diagonal line representing a neutron-to-proton ratio of 1:1. On the colored blue and orange band, the black center represents the most stable neutron-to-proton ratio. As you can see, for nuclei with fewer than 20 protons, the black center of that color band is approximately at the black printed line of a 1:1 ratio. At atomic numbers greater than 20, the most stable neutron-to-proton ratio is slightly larger than 1:1. Let's look at a sample problem. Determine the neutron-to-proton ratio of carbon-12, carbon-13, and carbon-14 and identify the most stable isotope. To determine the neutron-to-proton ratio of these three isotopes, we first need to figure out how many protons and neutrons each contains. The mass number of carbon-12 is 12, and its atomic number is 12. This means it has 6 protons and 6 neutrons, because the number of neutrons is determined by subtracting the atomic number from the mass number. The neutron-to-proton ratio is equal to the number of neutrons divided by the number of protons, which in this case is 6 divided by 6, which is 1:1. The mass number of carbon-13 is 13, and its atomic number is still 6. That means carbon-13 has 6 protons, and 13 minus 6 neutrons, or 7 neutrons, and a neutron-to-proton ratio of 7:6. Carbon-14 has a mass number of 14 and atomic number 6. That means it has 6 protons, 14 minus 6, or 8 neutrons, and a neutron-to-proton ratio of 8:6, which reduces to 4:3. Therefore, the most stable of these three isotopes is carbon-12, since, for nuclei with atomic numbers less than 20, the most stable neutron-to-proton ratio is 1:1. The band of stability can also help us determine which type of radioactive decay an unstable isotope will undergo. If the neutron-to-proton ratio lands in the yellow area, it means that the isotope is too heavy. An isotope that is too heavy will release alpha particles to reduce its size. Isotopes that land in the turquoise area have a larger neutron-to-proton ratio than is considered stable. These isotopes need to get rid of some of those neutrons in order to have a stable neutron-to-proton ratio. They do this through beta decay, in which, as you may recall, a neutron turns into a proton and an electron, thereby decreasing the number of neutrons and increasing the number of protons. By lowering the number of neutrons in the numerator of the neutron-to-proton ratio and raising the number of protons in the denominator of the neutron-to-proton ratio, it lowers the neutron-to-proton ratio. If an isotope falls on the orange line, which is below the black line of stable nuclei, it clearly has too few neutrons to be stable. In order to increase the neutron-to-proton ratio, a proton becomes a neutron. It does this through positron emission, in which a proton becomes a neutron and a positron, which is a positive version of a beta particle. In summary, this is how to determine the most probable type of decay a radioactive isotope will undergo. If the nucleus contains more than 83 protons, it is simply too heavy to be held together by the strong nuclear force and will most likely undergo alpha decay, because emitting heavy alpha particles is the quickest way to reduce mass. If the neutron-to-proton ratio falls to the left of the band of stability, meaning it contains too many neutrons or too few protons, the nucleus will most likely undergo beta decay, because in beta decay, a neutron is turned into a proton, thereby decreasing the number of neutrons while increasing the number of protons. If the nucleus falls to the right of the band of stability, meaning it contains either too few neutrons or too many protons, it will most likely undergo positron emission, in which case a proton is turned into a neutron, thereby increasing the number of neutrons and decreasing the number of protons. There is also something called magic numbers. Experimental evidence has shown that the number of nucleons, a nucleon can either be a proton or a neutron, helps to determine whether a nucleus will be stable. When considering magic numbers, the greatest influence on stability is having a positive number of both protons and neutrons. In fact, most nuclei containing both a positive number of protons and a positive number of neutrons are stable. In addition to having a positive number of protons and a positive number of neutrons, there are certain magic numbers that are especially stable. These numbers are, for protons, 2, 8, 20, 28, 40, 50, and 82, and for neutrons, 2, 8, 20, 40, 50, 82, and 126. This means that if the nucleus has one of these magic numbers of protons and or one of these magic numbers of neutrons, it will be especially stable. These magic numbers are assumed to correspond to filled nuclear shells. These magic numbers are similar to, but not necessarily the same as, the number of electrons in filled electron shells that give noble gases special stability. One piece of evidence to support this nuclear shell model and the existence of magic numbers is that many radioisotopes decay by alpha radiation. An alpha particle contains a magic number 2 for both protons and neutrons, which gives it special stability. In this example, we have the alpha decay of polonium-212. Notice how when polonium-212 undergoes alpha decay, it becomes lead-208. Lead-208 contains a magic number of protons, 82, and a magic number of neutrons. The number of neutrons can be determined by subtracting the atomic number from the mass number. 208 minus 82 is equal to 126 neutrons, which is a magic number. Therefore, we would expect lead-208 to be stable and to not undergo radioactive decay. To predict whether an isotope will be stable, follow these steps. First, determine if the number of protons and number of neutrons is an even number. Next, determine if the number of protons and/or the number of neutrons is equal to a magic number. Third, calculate the neutron-to-proton ratio. Check that neutron-to-proton ratio on the band of stability. If the neutron-to-proton ratio is on the band of stability, it is a stable isotope. If it's off the band of stability, you can then predict what type of decay it's most likely to undergo. Is calcium-40 stable? First, we determine if the number of protons and the number of neutrons is even, which they are. Second, we determine if there is a magic number of protons and neutrons. Calcium-40 has 20 protons, which is a magic number for protons, and 20 neutrons, which is a magic number for neutrons. So already we can see that this is a stable isotope. Let's continue anyway. Step 3 is to calculate the neutron-to-proton ratio. We do that by dividing the number of neutrons by the number of protons, and we get a neutron-to-proton ratio of 1:1. Finally, we take that 1:1 ratio and compare it to the band of stability. And we see that an isotope with 20 protons and 20 neutrons is indeed stable. Another sample problem. Is manganese-54 stable? We first check to see if the number of protons and number of neutrons are even. Manganese has 25 protons and 29 neutrons, so no, it does not have an even number of either protons or neutrons. Further, neither of these odd numbers is a magic number for either protons or neutrons. Finally, we calculate the neutron-to-proton ratio. The neutron-to-proton ratio is 29:25, which is about 1.16:1. We compare that ratio to what we find on the band of stability. Looking on the band of stability, it seems as if the ratio of 29 neutrons to 25 protons is indeed stable. Sample problem. Write the equation for the probable mode of decay of aluminum-28. To determine the probable mode of decay, we need to figure out where aluminum-28 falls on the band of stability. To do that, we need to determine the neutron-to-proton ratio. Aluminum-28 has 13 protons and 28 minus 13, or 15 neutrons. Therefore, it has a neutron-to-proton ratio of 15:13, which is equal to 1.15:1. It's hard to tell from this graph, but it seems as if this neutron-to-proton ratio falls in the blue section of our band of stability. This means it has more neutrons than is stable, so in order to reduce the number of neutrons, aluminum-28 will most likely undergo beta decay, turning a neutron into a proton and a beta particle. Finally, since we predict that aluminum-28 undergoes beta decay, we write the equation for the beta decay of aluminum-28. In beta decay, aluminum-28 gives off a beta particle. Knowing that the sum of the mass numbers on the right-hand side must equal the mass number on the reactant side, and that the sum of the atomic numbers on the right-hand side must equal the atomic number on the left-hand side, we know that the atomic number of our decay product is 14, and its mass number is 28. From the periodic table, we can identify this decay product as silicon-28.